Dear colleagues, let us start. It's a great pleasure for me to introduce our today's speaker, Professor Gunther Springholz from Johannes Kepler University of Linz. A few remarks about his career. He studied physics at the Technical University of Graz, graduated from there in 1988, and then worked for a couple of years at the Fraunhofer Institute for Solid State Technology in Munich. After that, he moved back to Austria and entered PhD studies. And in 1994, he graduated, obtained PhD degree, and continued working at the Johannes Kepler University of Linz as a postdoc first, then a university assistant, and soon from 1999 he became an associate professor at the Institute for Semiconductor and Solid State Physics at this university. And since then, he is leading research group working on group 4 to 6 semiconductors. And in particular, today's talk is devoted to very fascinating phenomena on ferroelectric Rashba type group 4 to 6 semiconductors. With this, I would like to pass the microphone to Professor Springholz. Please, the floor is yours.
Thank you very much. I would like to thank the organizers to invite me to this seminar, to which I've previously also participated in, and I think you have very good and interesting presentations in your program. So as Andre said, today I would like to give a short overview of ferroelectric Rashba semiconductors, which is a new type of material new type of materials which combine ferroelectricity and Rashba physics in one and the same material. And here below you see an outline of my talk. I first give some introduction motivation, then describe what is the basis of the ferroelectric Rashba effect, and discuss different realizations of that and the kind of investigations we have performed, and then in the end give some summary and outlook. So, oops. So here I would like to mention a list of my co-workers. So in my group in Linz, Gauthier Griezmann, who actually moved now to Paris, Tetiana Tsakosylo, or spelled wrongly, she's from Kiev, a PhD student from Kiev. Then our collaborators in Paris who have performed magneto-optical experiments, collaborators from the Swiss Light Source and the EPLF in Lausanne, particularly Juraj Krempasky, who did a lot of studies on the germanium telluride system. Also like to mention collaborators from IFPAN in Warsaw, Valentin Wolovuev, who was my postdoc, and he's now there working also on 4-6 semiconductors. People from Czech Republic, Jan Minar and his group doing DFT calculations in Renault EC-Tech, André Kaha and his group doing structural investigations, and the people at the synchrotrons Solaris in Krakow, where we have performed a lot of measurements that I'm going to show today. So as an introduction, basically every one of you knows electrons, they carry a charge, but also a spin. And for most of the applications, charge is the main property that is utilized, and that is because the flow of charge can be easily controlled by electric but also magnetic fields. So the charge manipulation basis of solid state electronics, and computer chips as we know today. However, the electrons also have a spin 1/2, and thus they also have a magnetic moment defined here by this equation. Basically, for a free electron, the magnetic moment is equal to the Bohr magnetron. And the spin, the existence of a spin of the electron was actually proposed theoretically by Gunsmith and Uhlenbeck in Germany back in 1925. And the existence of this, or the experimental proof of the existence of an electron spin was derived from the Stern-Gerlach experiments in the 1920s, where basically in a non-uniform magnetic field, the spin up and spin down electrons of silver atoms give rise to different trajectories, as is shown here. So it appear two spots on the screen because of the spin separation. So in order to utilize the spin also as information carrier, there's this field of spintronics that tries to use the spin properties of the electrons for data processing and data storage. But there's a problem. In most solids, the electronic states are spin degenerate, so that means each state is populated equally by spin up and spin down electrons. So basically, in most solid systems, there is no spin polarization of the electronic band structure. And also when a current flows, when electron flow through the material, there is no net spin current associated with it because an equal amount of spin up and spin down electrons flow in the same direction, and also the spin compensate each other. So to work around this, classical magnetoelectronics, they utilize magnetic materials to obtain a spin polarization. So that is one direction. The other direction is based on spin-orbit coupling, which is a relativistic effect. And this spin-orbit coupling usually can induce a spin imbalance in various properties of the system, be it in the spin polarization of the band structure, but also an imbalance in the flow of electrons with spins in the system. So in essence, as shown here in this cartoon here, spintronics tries to unite this charge and spin properties and create new functionalities by this combination. Now, classical magnetic spintronic materials are usually ferromagnets, as shown here on the left-hand side, where basically the spins or the magnetic moments are aligned in one and the same direction. So we have a net magnetization of the system, and this magnetization, this effective magnetic field, acts on the electrons, produces an exchange splitting of the spin up and spin down electrons, as shown here on the lower left side. So this breaks time inversion symmetry and induces a splitting of the electronic band structure in majority and minority carriers with spin up or spin down spin polarization. So this effect is usually used for GMR, spin valve, spin torque devices in magnetoelectronic systems, for instance, data storage with hard disk drives, etc. So there's been a lot of work to apply these principles also to semiconductors, and there's been a lot of work trying to make semiconductors magnetic by doping semiconductors with magnetic impurities. An example is manganese doping of gallium arsenide and manganese doping of other compound semiconductor systems. But it has turned out that it's really very hard or essentially impossible to produce ferromagnetic semiconductors with a Curie temperature near or above room temperature. This is not necessarily the case for antiferromagnets, where we have in the lattice compensated spin up and down magnetic moments, so there's no net magnetization. But antiferromagnetic semiconductors, insulators exist with Neal temperature well above room temperature. But the problem is that because there's no net magnetization, the electronic band structure is not spin polarized, so the spin up and spin down electrons populate the same bands equally. Nevertheless, it has been shown that there is also anomalous magnetoresistance effect, so the resistance changes as a function of current direction in the material, and you can change or manipulate the Neal vector, and then you also get a anomalous magnetoresistance response that can be used also for spintronic devices. More recently, also it has been shown that there's another class of magnetic materials that is of high interest for spintronic application, and these are called altermagnets. And they are basically antiferromagnets, but the magnetic moments, the local environment of the magnetic moments within the cage of the neighboring atoms is such that if you go from one lattice site to the next lattice site, you need not only to flip the spin, but also rotate locally the environment. So these systems have special rotation symmetry associated with that, and it has been shown that this gives rise to a spin polarization of the electronic band structure, is shown here in the lower right corner. If we integrate the spin polarization of the whole Brindleyon zone, the net polarization is zero, so that is similar to normal antiferromagnets, but along certain directions in K-space, the spin up and spin down bands are splitted in energy.
May I ask a question
Yeah.
about characteristic temperatures for altermagnets? Are they comparable to antiferro magnets usually?
Yes, yes. So we have studied manganese telluride, as shown here. On this slide, we have studied in more detail manganese telluride, which is according to this table here, published in this PhysRefX paper of Libor Snekal and collaborators. So for these altermagnets, the system has to show a particular symmetries. And here on the right-hand side, there's some candidates or materials listed, which fall into the different classes here. And here, for example, in this class C6S, which are called G-wave altermagnets, there's materials such as chromium antimonide, manganese telluride, and other materials. So there's also ruthenium oxide, which is also an altermagnetic with the Neal temperature above room temperature. Manganese telluride itself has a Neal temperature that is around 310 Kelvin. So here in the lower part, it shows some calculations for manganese telluride, the spin splitting according to DFT calculations, and next to it is some angle resolved photoemission experiments done in our group that shows the spin splitting that is theoretically predicted. And we have also looked at the temperature dependence, where one can see that at 320 Kelvin above the Neal temperature or critical temperature of the system, the bands are the paramagnetic states. These bands are not spin splitted, whereas if we cool down to low temperatures to the altermagnetic state, the bands become spin splitted due to the altermagnetic effect. Some different topic, and that is spintronics without magnetism. And the ingredients are that one needs material with strong spin-orbit coupling as well as broken inversion symmetry. And this broken inversion symmetry can either arise from the missing inversion or the inversion asymmetry of the bulk crystal lattice or structural inversion symmetry, as for instance occurs at hetero interfaces between two materials or in system where is a band bending towards the surface. So as has been shown by Emanuel Rashba, who was born 1927 in Kiev, actually, this gives rise to an additional term in the Hamiltonian, here this Rashba term. And the magnitude of this term is given by the so-called Rashba coupling constant that defines or that is depends on the strength of the spin-orbit coupling, but also on the strength of the inversion symmetry breaking. With this term, what happens is shown here that the electronic bands, here for an example for the case of a free electron system, splits up in two branches, the blue one and the red one. The blue one is the one with the spin up, the red one with the spin down, and they are shifted not strictly in energy, strictly speaking in energy, but in the k direction. And this splitting is quantified by this Rashba momentum splitting Kr, which gives the magnitude of how much this spin splitting is. For free electron system and for a linear Rashba effect, the energy momentum dispersion is then shown here by this equation here. So we have the free electron term h squared k squared over 2m plus minus alpha times the momentum of the electron and the absolute value of it. So that means we have this equation defines the two terms. Each one is parabolic, but is shifted by this Kr value. If you look here, we make a cross section at constant energy, and we look at the spin texture, the spin orientation at different kx in plane kx and ky points. We see we have two concentric rings formed by these two bands, and in each of these rings, the spin polarization has a hieral structure. So the spins point here from the to the right, and if we go around this 180 degrees, it points to the left, and then at 360 degrees again to the right. And so and in addition, these two rings of the two branches have a counterclockwise chirality of the spin texture. Here on the lower right-hand side, there's an example of actual measurements of the gold 111 surface using photoemission spectroscopy, where one exactly sees this Rashba splitting of the surface state of gold 111 due to the symmetry breaking caused by the existence of the surface. These experiments are usually done by, or the observation of Rashba effect can be directly done using angle resolve photoemission spectroscopy, as shown here on this, or exemplified on this slide here. So basically, one illuminates a sample with a monochromatic UV light, for instance, coming from a synchrotron source. And photons knock out the electrons inside of the material, and these photoelectrons are then analyzed using a hemispherical energy momentum spectrometer. And in this, we can obtain a two-dimensional map of the energy versus in-plane momentum, where the in-plane momentum is derived from the angular direction of the emitted electrons. So in this way, one can make these beautiful three-dimensional maps of the electronic band structure of various materials. Here, example for topological insulator, bismuth telluride and bismuth selenide. And here on the right-hand side, you also see the effect, the appearance of the Rashba effect on the surface of bismuth selenide induced by surface doping, where here you see the emergence of this Rashba splitting in the system. Now, how can we use the Rashba effect to do spin orbitronics? And that is, so the goal is here is to be able to convert charge current into a spin current and vice versa. And one ways how to do this is based on the Rashba-Edelstein effect or the inverse Rashba-Edelstein effect. And that is illustrated here in the middle here. So if we apply electric field, we slightly move the the bands in momentum by delta k in the direction of the magnetic field, the electric field. And that means that here this blue shaded region here of electrons are populated more than the ones on the inner circle with opposite spin polarization. So that means that the current flow is imbalanced in the spin polarization. So there are more electrons with the spin up as compared to the spin down, and that generates a spin current that is associated by the charge current. One can also do the inverse effect. We can inject spins, and then one would obtain a charge current generated by the spin injection, and that is called the inverse Rashba-Edelstein effect. Now, what is the magnitude of this effect?
My next question, how do you include these spins, realize this inverse Rashba-Edelstein effect? So
you need to inject spins in the system, for instance, by making a heterostructure with a heavy metal as a source. And then you inject spins, majority spins with one with a preferred spin orientation, or diffuse into the system spins from a side electrode, and this will generate then an imbalance in the population, and which induce through the system. So basically, it's just the inverse process of the Rashba-Edelstein effect, where the Rashba-Edelstein effect is you have a charge current that results in a spin current, and in the inverse effect, one induces a spin current that results in a flow of a charge current. What is important, the figure of merit shown down here. So it's Rashba-Edelstein length. That is the ratio between.
Another question about this picture.
Hello?
Can I have another question about this picture?
Yes.
So what is the meaning of the shifting of the circles?
That is the shift that is caused by the electric field. So you have to induce a charge current, you have to apply a electric field.
Right, but that means
and that means that you have a slight shift of the charges, or we have a stronger population on the one side, on the right-hand side, for instance, here of the Rashba bands than on the opposite side. And because the blue has a higher density of states, there's an imbalance in the spin current that flows together with the electron current.
So is that a shift of population or a shift of the band structure?
It's a shift of the population, strictly speaking, yeah.
Thank you.
So the figure of merit shown down here for a two-dimensional system is basically the ratio of the charge current to the spin current, and is proportional to the magnitude of the Rashba constant times the spin lifetime or spin scattering time. So that means to have a system with a large Rashba-Illeisten effect, you need a system with very large Rashba coupling constant and a high mobility or high low spin scattering time, which randomizes the spin population. Another mechanism that is also based on the spin orbit coupling is the so-called spin Hall effect. So if you pass a current through a system with a large spin orbit coupling, then there is an asymmetry in the scattering of the electrons as a function of spins. So spin up electrons with spin up are slightly more probably scattered in one direction than the electrons with the spin down orientation. And this gives rise also to a spin separation. So the up spins will go to the upper side, and the down spins preferably to the lower side here in this diagram. So that means in this case, we have a charge current and a spin current that is perpendicular to the charge current. And also here the inverse effect is possible. And the figure of merit here is defined by the often quoted spin Hall angle of the system. Now, as I said, we need a system with large Rashba constant to have a large Rashba-Edelstein effect. And a way to produce a system with very large Rashba constants is to use ferroelectric materials. This concept was introduced by Silvia Picozzi in 2013. So she kind of showed that in ferroelectrics, this Rashba effect can be very large. And the reason for that is that in a ferroelectric material, we have an electric polarization that breaks inversion symmetry. And this electric polarization can strongly enhance the Rashba effect in these systems. In addition to that, if you have a ferroelectric, there's a symmetry breaking by the ferroelectric polarization, which can point in the upward or downward direction. The electric polarization can be also manipulated and switched by electric fields. And it turns out if the electric polarization is in the upward direction, we have a certain chirality of the spin texture of the Rashba bands, for instance, in the clockwise direction. And if we switch the polarization in the opposite direction, the chirality is reversed, and we have the chirality of the spin texture in the opposite direction. And this is a non-volatile switching process because the polarization can be switched by an electric pulse and remains there as long as the polarization is stable in the system. So she has proposed as germanium telluride as a model system for this ferroelectric Rashba semiconductors. And germanium telluride is one of the simplest ferroelectric systems. It is shown down here. Basically has a rock salt cubic structure, which is slightly distorted along the 1-1-1 body diagonal direction. In addition to this distortion, the sublattice of the germanium and tellurium atoms are slightly shifted with respect to each other. And this shift is the origin of the ferroelectric polarization in this system. So here is shown here on this diagram the in-plane and out-of-plane lattice parameter of the system. So in-plane means perpendicular to the 1-1-1 direction, and out-of-plane parallel to the 1-1-1 direction. And one can see at a temperature of around 700 to 750 Kelvin, there is a structural transition from a cubic to a rhombohedral phase. The one is paraelectric, the cubic phase, and the rhombohedral phase is ferroelectric. So the TC is very high, well above room temperature. And in addition, in this system, there is a very large shift of the anion and cation sublattices of the order of 0.3 angstroms, which is about 8% of the interatomic distances in the system. So it's a very large effect. So they have calculated the electronic band structure by DFT calculations. And this is shown here. So the band extrema here are at the Z point of the Brillouin zone. So that is at the edge of the Brillouin zone along the 1-1-1 direction, parallel to the ferroelectric distortion axis. And here in this dashed circle here, one can see the Rashba splitting of the valence band, as well as the Rashba splitting here up here of the conduction band. And they also calculated the spin polarization of the Fermi surface, which, however, has this star-shaped form. And with the ferroelectric polarization along the 1-1-1 direction, we have the spin polarization as shown here by the red arrows here. And if the polarization is reversed, the spin polarization is in the opposite direction. So from these calculations, they can calculate the Rashba coupling constant alpha, which is basically a ratio between the Rashba energy indicated here by this red line here, and the in-plane separation ER and KR, and they derive a Rashba coupling constant of 4.8 EV angstrom, which is really a giant value, much higher than for normal semiconductors. Indium gallium arsenide, for instance, has a Rashba coupling constant that is about 100 times smaller. So we have studied this system using angle-resolved photoemission spectroscopy. So here on the left-hand side are our experimental results obtained using soft X-ray photoemission, angle-resolved photoemission spectroscopy using a photon energy of about 400 electron volt. At this high photon energy, the method is bulk sensitive because this is a bulk effect and not a surface effect. So for that reason, it is useful to use a bulk sensitive method. So this shows here cross sections here along a certain line in the kx direction as a function of excitation with different photon energies from 700 to about 300 electron volts. And here cuts, Kx and Ky cuts at certain symmetry points, the Z point and the gamma point of the Brillouin zone. And here on the right-hand side is shown the theory DFT calculations performed by Jan Minna's group in Pilsen, and one can see a quite good agreement between the experiments and the theoretical calculations. And from that, we can verify the Rashba splitting at the Z point of the Brillouin zone, as is shown here by the experiments, and measure the Rashba splitting in energy and in momentum. And we have derived from these experiments an experimental value of the Rashba coupling constant of 4.3 EV angstrom that is quite close to the originally predicted value. Now, we also measured the spin texture associated with the Rashba effect. The problem with that is that with soft X-ray RPES is bulk sensitive, but the intensity is very low, so it is not possible to do spin resolved measurements and measure the spin polarization of the emitted photoelectrons. For that, you have to go to UV, so-called UV APES, where the photoelectrons are excited with a UV light in the 10 to a few 10 electron volt range. The problem with that is that at low photon energies in the UV range, APES becomes very surface sensitive, and for most systems, there are surface resonance states or even surface states that are formed at the surface of most materials, and that means that in this UV APES range, the bulk band structure is superimposed by a surface band structure, and one can see this difference here by comparing these two images here. So in the UV range, we observe these star-shaped bands superimposed or in addition to the bulk bands. So it is a quite tricky thing to separate between the bulk contributions and the surface contribution, and the surface states also show a strong Rashba splitting, as it turns out. So and then one can measure here the spin polarization along certain cross sections of this map. This is shown here in the lower part, where is the intensity of the spin up and spin down electrons are plotted, and one can see the difference is proportional to the spin polarization, and that one can see that there's a strong spin polarization in this band structure, where in some places the spins preferably are in the down direction, and in the other parts in the upper direction, as is indicated here by the red and green arrows here. So this schematic is a results summary of the experimental data, and down here a comparison of the spin polarization obtained from theory, and one can see a very good agreement between theory and experiments. Now, in the system, there's also additional degree of freedom, because we can also induce ferromagnetism in germanium telluride by manganese doping. This is shown here. If we measure the magnetization as a function of temperature for different manganese doping levels, we see that there's a ferromagnetic signal emerging with a transition temperature that strongly increases with the manganese concentration. The maximum is 200 Kelvin for about manganese concentration of 50%. And here is shown the corresponding hysteresis loops recorded at low temperature for layers with different composition. If we add manganese, on the other hand, so if we add manganese, we get ferromagnetic response of the system, but on the other hand, adding manganese reduces the ferroelectric lattice distortion, as is shown here. So pure germanium has a very large rhombohedral distortion, which is proportional to the difference between the in-plane and out-of-plane lattice constant along the 1, 1, 1 and perpendicular to the 1, 1, 1 direction. So if we add manganese, then the splitting decreases, and at some concentration around 30%, the system becomes cubic at room temperature, because this is measured at room temperature. So from this, we have constructed a kind of multiferroic phase diagram, where in red here is the region of ferroelectricity indicated with the symbols here indicating the transition ferroelectric Curie temperature. Here in blue is the ferromagnetic transition temperature measured by squid, for instance. And in the green region here, we have a superposition of ferroelectric and ferromagnetic properties in which the system is multiferroic. Now, if you have this situation, then we have a system where we have not only the usual Rashba splitting of a ferroelectric system, Rashba system, that is this or a yellow term here in the equation, but we also have a ferromagnetic Zeeman splitting induced by the ferromagnetism of the system. So as is shown here, if we have a ferromagnetic system, we have a Zeeman splitting of the spin up and spin down bands. If we have a ferroelectric material, we have a Rashba splitting. If the polarization is here in this case in a Z direction, and if we combine both in the same material, one expects Rashba-Zeeman splitting, which is a superposition of both effects as shown by this equation here. Of course, the situation is more complex because the magnetization and polarization in principle can be not collinear, but in different directions. And so there's a complicated spin texture evolving as a function of how the electric polarization and the magnetic and the magnetization relative to each other. So here's an example of the measurements of germanium telluride with these Rashba bands here. And if we add manganese, then there's this Zeeman gap here opening, as is shown in this cartoon on the upper right-hand side. Moreover, we can manipulate the magnetization direction and the polarization direction by applying magnetic or electric fields. So we have done such experiments. We measure the spin polarization, for instance, here along the Z direction. We apply a magnetic field to the system to switch the magnetization from the up to the down direction. And we see indeed the spin polarization is also switched. And likewise, we can do the same by applying electric fields to switch the polarization from the up to the down direction. And we can also see that the spin polarization is reversed by this process. Now, germanium telluride is a system which has quite some limitation, and that is due to the fact that germanium telluride has a high density of germanium vacancies in the crystal lattice, and this gives rise to a quite high p-type conductivity of the order of 10 to the 20 per cubic centimeter. So actually, strictly speaking, it's not a ferroelectric semiconductor, but also can be viewed as a ferroelectric metal because the Fermi energy is quite deep into the conduction valence band. So this high conductivity makes also the ferroelectric switching rather inefficient. This hole doping reduces also the Rashba effect and ferroelectric distortion as shown in these calculations. So if the system goes from N-type here on the right-hand side to P-type, the sublattice shift decreases and the system goes towards the cubic phase where this rhombohedral angle would be 60 degrees. So this in total limits the spin charge conversion efficiency, and this is one of the limitations of the system. Another effect that I mentioned is that in germanium telluride we have these strong surface bands appearing on the surface of the material. So we have a bulk Rashba effect superimposed by a strong surface Rashba effect, and that is always difficult to separate between these two different contributions experimentally. So we have looked for alternative ferroelectric Rashba materials. Actually, there has been some recent publications by Alex Zunger's group, inverse design of compounds, the ferroelectric and Rashba functionality. And in this paper, they published a table with more than 52 compounds. They predict to be ferroelectric Rashba semiconductors. But as you see from this table here, germanium telluride is really the material with one of the highest predicted Rashba constants. So our approach, instead of making all these new materials, which are not so well known, how to grow them and prepare them experimentally, we take a different approach. We take a look at the phase diagram for 6 materials, group for 6 materials, consisting of the lead chalcogenides, germanium chalcogenides, and tin chalcogenide compounds, germanium, such as germanium telluride, lead telluride, and tin telluride. And we can see here in this diagram that some of these compounds have ferroelectric properties, such as germanium telluride and also tin telluride, which is at the border. The lead compounds, chalcogenides, are mostly cubic, and tin selenide sulfide, germanium selenide sulfide, also can display an orthorhombic structure. So that means if we start from a cubic material such as lead telluride, we could add germanium telluride or alloy germanium telluride into lead telluride and cross the border from the cubic to a ferroelectric rhombohedral phase, and hope to retain the good semiconducting properties of lead telluride, which exhibits very high electron and hole mobility at low temperatures, and induce ferroelectricity by introducing of germanium atoms, very similar to the approach to produce a ferromagnetic semiconductor by taking a gallium arsenide as a semiconductor host material and adding manganese to the system. Limitation of this approach is that it is known the solubility of germanium telluride and lead telluride is limited to about 10–20%. And due to this limited solubility, in order to introduce a feasible amount of germanium into lead telluride, one needs to apply low temperature growth. We do this synthesis using molecular beam epitaxy. We have here a lot of different materials we can synthesize with our systems. So, we use here germanium telluride source to dope lead telluride epitaxial layers, and with concentrations up to almost 15%. And so what we see when we do X-ray diffraction as a function of temperature, so this is shown here. Here we're looking at the 222 Bragg reflection of lead germanium telluride, and from down black to purple, the temperature is lowered from 300 Kelvin to 70 Kelvin. We see that at some temperature, the peak starts to split up in 2 peaks. This is also shown here in the reciprocal space map, where at low temperature, the X-ray peak of lead germanium telluride is split in 2, whereas above at room temperature, there is just 1 peak. So this peak splitting indicates the ferroelectric phase transition, where the cubic lattice is distorted along the 111 direction, and there's a slight rhombohedral distortion of the lattice, and that is the reason for this emergence of these 2 peaks. And if you measure this transition temperature as a function of germanium concentration, you can see this phase diagram where in the upper part the system is cubic, and in the lower part, in the red part, it is rhombohedral. So at 15% of germanium, we can achieve a TC of around room temperature. What is important, this rhombohedral distortion alone does not tell anything about the ferroelectric properties of the material, because ferroelectricity comes not from the distortion of the cubic lattice, but rather by the lateral shift of the sublattice, is indicated here by this red arrow here. So meaning that in the ferroelectric phase, the anion and cation sublattice have to be slightly shifted with respect to each other to produce the ferroelectric polarization that is the important property of a ferroelectric material. So this sublattice displacement can be measured by measuring the intensity of odd Bragg reflection as a function of temperature, as is shown here, and one can see that with increasing germanium concentration, there is a deviation from a constant value of this intensity ratio, and this deviation from this constant value is the onset of the ferroelectric phase transition. But one can also quantify this sublattice shift by evaluating this intensity ratio using this equation here. And the result is shown here on the lower right-hand side. So we can quantify the sublattice shift as a function of temperature, and this follows nicely Ginzburg-Landau theory of second-order phase transition, where the sublattice shift as a function of temperature is a constant times the square root of 1 minus T over Tc. And this sublattice shift, with this non-sublattice shift, we know that the electric polarization is proportional to it, because the sublattice shift times the ionic charge of the anions and cations gives directly the electric polarization of the system. Now I would like to speed up here a bit. So we have measured the ferroelectric Rashba effect in lead germanium telluride, as is shown here by this experimental data. So for 6 semiconductors have a many-valley band structure, is shown here on the right-hand side. So the band extrema at the L point of the Brillouin zone, and we have one along the ferroelectric polarization direction, which is called the Z point, and we have the M points, which are the projection of the oblique valleys to the surface Brillouin zone, as shown as indicated here in the schematic diagram. So at low temperature, we again find this Rashba splitting, both at the gamma point and the M point, where we observe that at the M point, the Rashba splitting is obviously larger. And we can compare this to the measurements for lead telluride without germanium doping, and we see at low temperature, this Rashba splitting is completely absent. We can also look at this as a function of temperature. This is shown here for the M point. So if we take lead germanium telluride above 200 Kelvin, there is no Rashba splitting of the valence and conduction band. Then when we cool down the system, there is the emergence of the Rashba splitting, and the Rashba splitting increases the lower the temperature. And this is exactly a result of the fact that as the temperature decreases, the ferroelectric polarization, and the sublattice shift increases and saturates at low temperature to this delta zero value. And again, we can compare this with paraelectric lead telluride, which has no ferroelectric phase transition. And we see that at any temperature, the bands, the electronic subbands are not splitted. So meaning that the spin polarized, these bands are not spin polarized at any temperature. We have also developed a model of the Rashba splitting of the band structure using K.P theory. This is a theory developed by postdoc Gauthier Griezmann, and he extends the usual K.P Hamiltonian of for 6 materials by these red terms here, which describe the effect of a ferroelectric polarization and symmetry breaking of the system. And here are some examples of the calculations here for the gamma point. So in the paraelectric phase, we have a certain band gap delta 1. And if we switch on the ferroelectricity in the system, we have a change of the band gap as shown by this delta 1 tilde, as well as a lateral splitting of the bands. These are the electronic subbands because we have a thin film system, a quantum well system with various subbands. And we see that each subband is splitted by the Rashba effect. And if we compare this to the experiment, we have again a nice agreement between theory and the experimental results. I should also point out that because we have here a narrow gap system, the bands are not parabolic as indicated here, but they have massive Dirac energy momentum dispersion is shown here. And for that reason, the Rashba parameter is different compared to the usual derivation for a free electron system. So this is the correction term here that comes from the deviation from the parabolic band structure. The same model is we applied for the endpoints. And again, we see here a very nice agreement. So the blue lines are the calculations and the red lines, the measurements. And from this, we can extract the Rashba parameter as a function of temperature at the endpoint. And we obtain a value of 2 eV angstrom for the germanium telluride sample with 7% of germanium, which is half of the value of germanium telluride. So it's a little bit lower. But in this case, we can make the system P and N type, dope the system P and N type, and we also obtain a much higher electric mobility of the system. We can also compare the atomic displacement that we obtain by X-ray diffraction and with the displacement obtained by evaluating the Rashba splitting. And we find, as shown here, both of these parameters follow the Landau-Ginzburg theory of a first-order phase transition, so follow exactly the same behavior. And we find that the Rashba constant depends basically linearly on the ferroelectric sublattice displacement of the system. Now, just shortly, what happens if we increase the ferroelectric polarization or lattice distortion? Then this Rashba splitting gets larger and larger, as shown here. So these are curves calculated at the set point for different ferroelectric polarizations and different magnitude of the Rashba parameter. So one can see that if alpha gets larger and larger, we have here a stronger and stronger downward shift of the minima of the band gap. And evidently, if alpha gets very large, then this band gap here closes completely, and this gap closing occurs if the Rashba energy gets larger than half of the band gap of the system. This is shown here on the right-hand side. So basically, this is forms a circular nodal line of a zero gap semi-metal where the gap is completely closed. Now, how can we achieve such a? We can either increase the Rashba constant so that this gap here becomes closed. So that means we would need to dope more and more germanium, but the germanium solubility is limited. But we can also do the other way around. We can reduce the band gap of the system so that it is more easy to achieve this condition that the Rashba energy gets larger than the band gap of the system. This is can be achieved by adding tin to the system. So if we go from lead selenide or telluride to lead tin telluride or lead tin selenide, the band gap of the material decreases and crosses zero at a certain concentration, which is about 16% for the selenide system and 36% for the telluride system. Actually, in this direction, we have a transition from a normal insulator semiconductor to a Dirac semi-metal system to an inverted band structure showing topological crystalline insulator properties. But here we remain in this regime where the band gap of the system is very small, so it is easily achieved that the Rashba's energy is larger than the half of the band gap. And the interesting physics occurs here at the oblique valleys of the system that is shown here, the calculations where one finds that instead of this ring, we have 4 band crossings, band minima here at these points here that are split in momentum, and this indicates the emergence of a while phase of the system, a new while phase with 4 while nodes appearing at each of the band extrema at the L points of the system. So then one gets this kind of phase diagram. If we increase the tin concentration, we go from a normal insulator to a topological band inverted insulator. Without ferroelectric polarization, we would go simply to a band closing at this point here. But if we have, in addition, a ferroelectric polarization, and we follow this path here along this red dashed line, we go from a ferroelectric Rashba semiconductor into a while semi-metal state to a ferroelectric topological insulator. And this is a modeling here of this, or prediction of this phase diagram for the case of them, where we have lead selenide as a host material. Tin is added to reduce the band gap, reduce ferroelectricity of the system. And here are some first magneto-optical Landau level spectroscopy results of this material that we have produced in our group. So let me summarize my presentation. So I hope I have given you a flavor of what is behind the term ferroelectric Rashba semiconductors. The basic essence is that due to ferroelectricity, this material can display a giant Rashba effect with very large Rashba constant. The spin texture can be programmed by the ferroelectric polarization, so you can switch by the ferroelectricity the chirality of the spin texture. And if you look at transport in one direction, changing the ferroelectric polarization would also flip the polarization, spin polarization of the current in the using K dot P and Landsberg theory, one can quite well explain these properties in the case of lead germanium telluride and lead germanium selenide. And we can also dope the system with magnetic impurities to induce ferromagnetic and ferroelectric properties at the same time. And this gives room to quite a large number of effects, Rashba-Simon effects, that is where the band structure is very much entangled between by the different possibilities of the direction between the magnetization and electric polarization of the system. And last but not least, I have shown that combining ferroelectricity and a zero gap material, this gives also an interesting route towards realization of while fermion system, where the presence of the while phase is controlled by ferroelectricity in the material. So that's all for my presentation. Thank you very much for your attention, and I'm open for questions.
Thank you, Professor Springholz, for a very inspiring talk. Now we are open for questions. Maybe I could start. You, in this slide, you mentioned this conversion efficiency of spin and charge. Are there any estimates, current and potential estimates for this efficiency?
For germanium telluride, there have been some works here shown here, just copied from the literature. There's a group in Milano of Christian Rinaldi and Riccardo Berdacco that have made this device and demonstrated ferroelectric switching in these devices, and they give a rough estimate of the spin to charge conversion efficiency. As I said, the spin conversion germanium telluride case is not limited by the large Rashba coupling constant, but by the spin scattering, by the small spin scattering time, because the system has a lot of vacancies and there's a large number of scattering centers in the system. For lead germanium telluride, we have not yet estimated or experimentally measured the spin charge conversion, because we have to produce a device where we have a spin readout of the spin current and measure that relative to the charge current, because the conversion efficiency, as shown here on the slide, is for that you have to measure the ratio between the charge and the spin current in the system. So we have to build a device where you have a charge current induced through the system, and then you need spin detectors such as platinum electrodes at which you can measure the spin current induced by the charge current of the system, and then the ratio is the figure of merit of the Rashba-Edelstein conversion coefficient.
Okay, but you expect that it should be larger for your system than this conversion?
As I said, the Rashba constant of lead germanium telluride is only half of that of germanium telluride, but the mobility is a factor of 100 or 1,000 times larger. So I expect the spin scattering time to be longer, and therefore get a higher figure of merit of the system.
Thank you. We have a question from Sergei Shevchenko.
My question is quite general. In quantum mechanics, spin-orbit coupling appears as a relativistic correction, so as a perturbative correction. Now we know and we can see that it's not small. It's not simply related to the ratio of velocity over electron velocity over the velocity of light. And now it's the base of, as you showed, not only spintronics, spin-orbitronics. What makes spin-orbit coupling large? Can you summarize?
Yeah. So basically, for large spin-orbit coupling exists for materials with heavy elements, because usually the spin-orbit coupling is larger when the order number of the elements increases, because they have a stronger overlap, a larger charge of the nucleus, and stronger overlap of the electron cloud with the nucleus. So that's one key element. So that's the reason why, for instance, graphene, which is a light element just of carbon atoms, the spin-orbit coupling is very small. As you noticed here, lead telluride, for instance, lead is a very heavy element, so that certainly helps in having a large spin-orbit coupling, and this spin-orbit coupling enters into the Rashba coupling constant. The larger the spin-orbit coupling, also the larger the Rashba constant will be. But it's not the only factor. Also the degree of symmetry breaking plays, or how the symmetry is broken in the system, plays a role that determines the magnitude of the Rashba constant. So there and these symmetry breaking mechanisms can be completely different. In the case of ferroelectrics, it's the displacement of the sublattice atoms. In the case of zinc blended semiconductors, you have a structural, the crystalline inversion asymmetry, because the crystal structure itself is not in inversion symmetric. And then you have thin film heterostructures and thin film systems, where at each interface you have an asymmetry of the band structure, because when the band structure from one material evolves into the band structure of another material, you always have gradients in the band edges, and that these gradients in the band edges are similar to an action of an electric field and depend on growth parameters, orientation of the surface or of the interface, and many other parameters. So it's very difficult to give a general effect. The only general answer I can give you is that heavy materials with heavy elements usually always have a higher spin-orbit coupling than compared to compounds with light elements.
Yeah, thank you.
Thanks. Well, I do not see other questions at this moment. So, I see the one from Valentin Volobuev. Please go ahead.
Hi, Gunther. So my question is because if you remember, I as well was working in this germanium telluride, manganese telluride. So basically, it's interesting that it's finally found that it is this manganese telluride altermagnet. But we know, as far as I remember, that this altermagnetic, I would say, at least antiferromagnetic phase will be present if you dope like with germanium, like if you put in manganese telluride germanium. So did you do some research in this direction? Was it successful? Maybe
no,
you
we
as
have
well
not.
can.
I mean, if you look at the phase diagram for lead germanium, germanium manganese telluride. So we have manganese telluride on one side, which is altermagnetic, germanium telluride on the other side, which is purely ferromagnetic. But at 50% is the solubility limit. If you go with higher than 50% manganese, you have a two-phase region where you have manganese telluride plus some precipitates of germanium manganese telluride or others or other precipitates. So it's no longer a well-defined uniform system. Concerning the altermagnets, I would like to mention one problem with altermagnets or antiferromagnets in general. So for a ferromagnet, it is relatively easy to manipulate the magnetization by just applying a magnetic field, and you can reverse the magnetization from one direction to the other direction. Here there is the problem with antiferromagnets. So with antiferromagnets, the antiferromagnetic domains do not have a net magnetic moment. So if you apply a magnetic field, it is very difficult to rotate or manipulate the nail vector. This is what you need to do or to achieve the manipulation of the nail to create a functionality like switching of spin currents, etc. If you are not able to control or manipulate the nail vector direction, then this is difficult.
Okay, thank you.
Thanks. Yeah. By the way, are there any examples of ferromagnetic compounds which could also show some?
We have studies some time ago, europium selenide, for instance, which is a classical ferrimagnet, but the critical temperature is only 4.5 Kelvin, so it's not so easily accessible by for instance photo emission spectroscopy or methods like this.
I see. Thank you. So with this, I think we could finish. Thanks again for wonderful questions and answers session and for a beautiful talk.
Thank you.
Yeah, and
Thank you very much.
yeah, using this occasion, I would like to wish our speaker and all participants joyful holidays and happy New Year. We'll see each other then in 2025.
Yeah,
That's it.
I hope so.
Next year.
Happy New
Yeah.
Year and yeah, Merry Christmas. Goodbye.
Thank you. Goodbye.
Bye bye.
All right.